Hi everyone. This episode's been a while, hasn't it? Um, I'm really sorry. It's just with everything that's been going on, I've just not really been able to find the time. I've also been thinking a lot about how I make videos, and I've also been learning how to use things like GitHub to make the whole process of making these tutorials a lot easier. So hopefully, next episode shouldn't be too long now. I promise. Alright then, let's get to the actual video. In the last episode, we worked on a transformation matrix to take in the raw vertex data, a position, rotation and scale, and turn that into a 3D transformation. Now, this isn't the only type of matrix that we can use, and we're going to be learning about the other ones today. But first off, let's say we have a square in our current engine with a Z position of 0, and let's say we wanted to move that away from the camera. And in a 3D space, we would see that object getting further away and it would get smaller. But if we increase the Z position as it is now, nothing will change. Our engine has no depth. And that's really important for a 3D game, surprisingly. So, what we can do is we can use what's called a projection matrix. And this takes in a near plane, which is at what point closest to the camera that objects would begin to get cut off and excluded from the render pass. And also a far plane, which is the opposite, how far an object has to go until it's considered impossible to see. And we also have the field of view, which is how far around the 3D space a camera can see. Now this is just to make sure that everything is lining up correctly on the screen. In order to actually move around a camera, we need a view matrix, which takes in a position and a rotation and outputs a direction that the camera would be facing. And these two matrices combined will give us a 3D scene. So what we're going to do is we're going to create a camera class, which will contain a position and a rotation, not a scale. I don't know why I put that. And it's also going to have our field of view, near plane and far plane. The top variables will go into the view matrix, the bottom variables will go into the projection matrix, and they'll both go into a new render function in our renderer, and that will produce a 3D scene. So let's get to it. So as you might remember from the last episode, we had the engine in this kind of state. So we had our text showing up, and we could move it horizontally and vertically, but we couldn't move it on the z-axis. As you can see, I've got some code here that is actually changing the z position, but nothing's happening. So, first thing we're going to do is we're going to get rid of that stuff. Then we're going to just going to clean up some of these tabs. And the first thing that we're going to do is we're going to go into our maths class and we're going to make some more public static functions. This time we're going to make one that returns a matrix 4 and it's called create projection matrix. And all we have to do for that is return matrix 4 dot create perspective field of view, and this will tell us everything that we need to give the function in order to output a reasonable projection matrix. So we'll just put all that stuff in. We're going to give it a reference to the current window because we're going to need that to make the aspect ratio. So, plane, our plane, and anything else? Nope, that's everything. So to create the aspect, all we have to do is func aspect is equal to w.size.x. Make sure you're converting that to a float, otherwise it's not going to work. Divided by window size y. And we can just put everything in like so. And that's our projection matrix done. Now let's make a function for the view matrix. So once again, return matrix for dot create. No, sorry, it's not create, it's look at. And for this we need the I, which is the position of the camera, let's say, target, which is where the camera is looking, and up just being the up direction no matter what the camera's position is. So we'll make some variables, camera position, x3, camera target, and that's all we need for that. And for the up vector, all we really need is a vector 3 that is just 0, 1, 0, so 1 on the y-axis. That's everything there. But it's going to be annoying to have to keep the position and target of the camera always in just some sort of update loop. So what we're going to do is going to make a new class. I'm going to call it camera. But it's a public class, not static this time, because we may need multiple instances of this in the future. So what's this camera going to need? It's going to need a vector 3 for its position. It's going to need some rotation axes, which we're not going to call Euler angles in this case, we're going to call them pitch, yaw, and roll. Oh, sorry, I forgot to state that they are floats. And if you know anything about aeroplanes, you'll know what these are. Trying to think if we need anything else. We're also going to need some private vector 3s. Well, actually no, we'll make them public. This is going to be the right vector, which basically defines which, depending on the way the camera is facing, what is its right kind of direction. Imagine you're holding out your right arm and you're spinning in a circle. Your right vector would be the direction that your right arm is pointing. It never changes in relation to you, but it changes in relation to the world as you're spinning around. So we're also going to need one for the forward. So your arm is out in front of you and up. Your arm is up, like straight up as you're like bowing down, let's say. So just take these top ones and go into quick actions and refactorings and generate a constructor. And we're also going to add in reference to the window. Because what we can do is, if we don't want to update um, a class in the window class all the time, what we can do is take in that Windows update frame function, and just like when we did that with our own functions in the window loop, we're going to do plus equals, press tab twice, and get this little function that we're going to call update temp. And in this update function, all we're going to do is we're going to use the pitch, yaw, and roll, and we're going to generate these right, forward, and up vectors using a bit of maths that I don't remember, so I'm just going to look at my examples. So here's the code that generates the forward vector. We take in the pitch, remembering to turn it into radians, because you can't really do these kind of functions with degrees. And if you multiply the cos of each of the yaw and the pitch, that gives you the x value of the forward vector. Then sine of the pitch gives you the y, and cos times sine of the pitch and yaw gives you the z. And once we have the forward vector, it's really easy to figure out the others. Make sure that you normalize forward vectors so that you don't have any weird math. Sorry, that's the wrong function. So then you can figure out the right vector by just doing the cross product, which I don't really know what it does. I'm going to be honest. Of the vector3.unit_y, which is just the same as in our maths function where we do vector3, 0, 1, 0. It's just kind of a shorthand way of doing it. And it's the cross product between the unit y and our forward vector. Remember to normalize it again. And just copy and paste this because it's very similar to get the up vector. This time you just put the right instead of unit y. And that should give you everything. That's our camera class basically done. So now we can get to applying these matrices that we've made into the shader. So go over to testshader.vert, and we're going to make some more uniform matrices. So uniform map for friction matrix and uniform map for view matrix. So if we do the transformation matrix times view matrix times projection matrix, specifically in that order, that will give us the position that we want. And now we can load these in the renderer. So we need the render function to also take in a camera. And when we load in these matrices, actually, first things first, we need to not transpose that matrix anymore because we're now multiplying them in this order. You can actually just duplicate this twice. Matrix, matrix. And we're going to leave projection matrix for now. Let's do the view matrix first. Just take in cam.position, and for the target you just do cam position position plus cam.forward. And the only other thing, actually no, that's it, just close the brackets. And for the projection isn't really going to change in a game unless you're doing some things where the field of view zooms out when you're moving faster. That's kind of a thing that you can do. If you think you're going to end up needing to do that, then you can put the projection matrix in there every frame and it'll work just fine. But for us, it's going to be a lot more efficient if we just make the projection matrix once. So we'll do a public static matrix for making sure to import the right library, which calls projection, and all we'll do is when we first make the renderer, we'll make a public static void create projection, and we'll just do projection is equal to maths dot create projection matrix. We're going to set the FOV to be about 60, window to be, oh, we're going to have to take in the window. Near plane 0.1 and far plane, let's say 1000. And all we have to do is then put in the projection there. And now we can go over to the window class and at the top here, let's say camera, main camera, and in our load function we'll make that camera. My Visual Studio has been really laggy all of a sudden. New camera. Position, we'll just say it's vector3.0. Pitch 0, yaw 0, roll 0, and window this. Also need to make sure that we initialize the renderer by creating the projection, pressing in this again. And then just put the main camera in like that. Now this should be working, but chances are we might not see anything right when we press play, because it might be that it spawns behind the camera. So let's find out. Okay, what went wrong here? What didn't it like? Okay, apparently 60 degrees of vertical field of view is not correct. Problem is, in Blender, it uses horizontal FOV, so maybe we should just make a function that we'll call that create projection matrix vertical, and we'll make a new one that takes in FOVX. I'm going to go find some maths that allows us to convert it. Okay, I found some maths. So first thing you do is you take in the FOVX, you turn it into radians, and you do the arctangent of the tangent of half FOVX, divide it by the aspect, and then times it by 2. I don't understand it, but it works. So put in FOVY res. Also, I completely forgot to convert that to radians. That might actually be why it didn't work in the first place, but I prefer horizontal FOV anyway. So let's go back to the renderer. We'll do create projection matrix horizontal, and let's see if it runs. Okay, it ran, and we can't see anything. I'm assuming that's because it's behind us. So let's try and fix that. What we'll do is we'll just increment the main camera's yaw by 360 times our delta time. That should hopefully work. Let's find out. So we should be spinning right about now. Hmm. Hey everybody, I've got it working now. Turns out these are actually meant to be set to true. I was just an idiot. So, if I slow this down a lot, in fact, if I just get rid of it completely. So that's -10. It's gone again. Okay, there it is. There it is. We did it. And it is convincingly getting further away and getting smaller. So if we bring it a bit closer, it should be a lot bigger as it pans across the screen, hopefully. Hey, there we go. Alright then. So the last thing we want to do before we finish this episode is make a little panning camera kind of thing that you see in game engines like Unity. So the way we can do this is using those forward vectors and right up vectors that we got earlier. What we can do so what we can do is in our update frame function, do if mouse state dot is button down mouse button dot which one is it? Middle. There we go. And just to make sure Make sure that the window is focused. And what we can do is in camera dot yaw plus equals the mouse state dot position dot x minus mouse state dot previous position dot x times it by about 0.1. Just duplicate it for the pitch, find y and previous y, also times it by 0.1, but just do minus equals because obviously the y coordinate is switched in OpenGL to what you might be used to in Unity. And let's see if that worked. Should be able to scroll around to wherever texture is, and there we go. Look at that. It is kind of hard to view it as a 3D scene, but trust me, it's 3D. Maybe it would help if I spun the square around a little bit. We'll get some movement coded in as well. So if keyboard state is key down, is key down, yeah. Keys dot A, and we'll just do main camera dot position plus equals, who knows, yeah, minus equals main camera dot right times time dot delta time. Duplicate that so it's D and plus equals. Select them both. Duplicate again. The W, in that case, that's going to do plus equals the forward vector. And S will be minus the forward vector. And once more, for Q, it's going to be plus equals the camera's up vector. And E is going to be minus equals the up vector. Okay, let's give this a go. Obviously it's going to be pretty hard to tell the difference without where is it? I think I've lost it in the void. Alright, there we are. I don't know how I managed that. But yeah, as you can see, when we press the keys, okay, left and right is mixed up. But as you can see, we now have proper... Okay, switch those around, that's really disorientating. It seems like I am actually doing the right vector wrong then, because A should definitely be taking away from the right vector. I'll just try and figure that one out in my spare time. But yeah, as you can see, we now have a 3D moving camera. You can see the objects move around as you would expect in 3D space. And there we go. I think that's everything I've got for this tutorial. Next episode will be coming out hopefully much faster, and we're going to be doing OBJ loading next week. That's going to be awesome. Looking forward to that one. So see you all very soon.